Welcome back to the course on fluorescence spectroscopy, principles and biomedical applications. This is part B, where we're going to talk about the origins of anisotropy at a molecular level and time-resolved anisotropy decays. In the previous lecture, we just described anisotropy, how you would measure the steady state anisotropy. We never discussed in terms of what were the transition moments looking like in the molecule. So that's where we're going to start today. So first, to do this rigorously, you have to do a whole lot of trigonometry. And this is not the best format for presenting trigonometry. So I'm going to talk my way through this slide in sort of a hand-waving format. What we're interested in really is the projection of the transition moment. This is now the emission transition moment onto the z-axis and onto the x-axis. The x-axis is going to also represent the y-axis because we'll always have symmetry around the z-axis, and this cosine of theta actually going to represent a cone that's being excited. So you have to go through this calculation. First, we're going to go through it for a single fluorophore oriented along the z-axis, and then we're going to generalize it to a random distribution of fluorophores. In order to do this type of calculation, you have to take into account the number of molecules which are present in some d theta value around the z-axis, and that's going to be given by the probability distribution for the excited fluorophores. So there's a way to get that. And the next step is you go through all the trigonometry, and so basically I'm done with the hand waving. This is the equation that we come up with. That is always the case. The anisotropy is given by the cosine squared of theta, and it's 3 cosine squared of theta minus 1 divided by 2. This is always true. Now let's look at this single molecule. If this is oriented along the z-axis, then theta is 0, and if theta is 0, cosine is 1, so this becomes 2 over 2 and 1. So this states that if you can put a single fluorophore right on the z-axis, you will measure an anisotropy of 1. Or conversely, if you can orient your sample in such a way that all the fluorophores are pointing in the same direction, you'll be able to find an anisotropy of 1. But when you do this calculation over a random distribution of immobile, and I stress that at the moment, immobile fluorophores, we wind up with a maximum value of 0.4. So that's where this magic number comes from. It is purely a result of the cosine squared photo selection that we described in the previous lecture. So there is nothing atomic or molecular about this value at all. It's simply a result of how we're doing the measurement. Oh, I think I've adequately described this slide, which saying we're getting a cosine squared of theta by integrating over the probability distribution. I wanted to prove to you that this actually occurs in practice. Now, measuring the polarization of a single molecule, I guess it can be done and has been done, but it's rather difficult. But it was done easily using crystals, and these were crystals of green fluorescent protein. We've spoken about it before, and here we have a fluorescence microscope image of crystals of green fluorescent protein, where the arrows indicate the direction of the emission polarizer. What is the emission polarizer looking at? And then that's rotated, and when you rotate that, the intensity goes all the way down to 0, up to a normalized value of 1, down to 0 again. So that proves our assertion that if you had a single molecule around the z-axis, you could get an anisotropy of 1, but you'll never see that in practice with the random distributions that you looked at. So now that we know what anisotropy looks like, we ask ourselves the question, what does the anisotropy spectrum look like? And what we mean by the anisotropy spectrum is normally this is something you would use in a frozen glass solution of some propylene glycol, ethylene glycol, because you have to stop the molecule from moving and you have to put it in a solvent that it dissolves in. So if we do this for green fluorescent protein, we find nothing very interesting. Basically, the anisotropy is with an experimental error flat across the emission band and sort of flat across the absorption spectrum. But that's only true for very few molecules. And this is the much more common result of looking at anisotropy spectra. So here we have the fluorescent probe DAPI. In this case, it's been put in a PVA film. With PVA, after you've evaporated the solvent, you can stretch it and orient the system. Here's the absorption spectrum PVA. And this is sort of a common behavior of many fluorophores, is they have an area where the fluorescence is high, near 0.4. So at the lowest energy transition, normally the absorption and the emission oscillators are parallel to each other. And as you move into the first or the second excited state or higher, you see the anisotropy waver from 0.4, which means that on excitation, the transition moment is at a different angle from the transition moment in the ground state, assuming the ground state is along the long axis. When you get to S1, it might be at some other axis in the molecule. But because of Kasha's rule, the molecules always emit from the lowest singlet state down to the ground state. And for the lowest wavelength absorption, we always have a flat anisotropy. Okay, why is that anisotropy not, I can't go back on this program. Why is the anisotropy different from 0.4 if that's where many of the transition moments are localized in the ground state? And that's because there's another angle we have to consider. It's the angle that I was drawing on the previous molecule, saying, well, we have an absorption transition moment and an emission transition moment, and these need not be equal. When we were going from the lowest, longest wavelength absorption, these two were pretty much parallel, and we had an anisotropy of 0.4. As we went to shorter wavelengths, the anisotropy went down, and that's because there's an angle between the absorption and the emission oscillator, and that's where this term comes from. We call it beta. Beta is the angle between the absorption and the emission oscillators. So this equation is simpler than it looks because the fundamental anisotropy of any molecule is 0.4, which is purely a geometric factor, and then we have this cosine squared of beta, where beta is this angle, which determines the R0 value or the anisotropy value without any molecular motion at all. Here we've listed some values that are possible. We can look at either the anisotropy value or the polarization value. As we indicated in the previous lecture, they measure the same thing, just a different expression form. For a zero angle, maximum anisotropy is 0.4. If we put it in polarization terms, it's 0.5. But the anisotropy terms are nicer. If they're 45 degrees, we wind up with 0.1. We're going to see that this is called the magic angle. If that's the angle between the absorption and the emission oscillators. The anisotropy is 0, and if it's 90 degrees, the anisotropy is minus 0.2. 90 degrees would be just like that. So as an exercise, you could do this for yourself. Assume the cosine squared, assume beta is 54.7, and go through this calculation, and you will see that you wind up with a value of 0 for the anisotropy. Some fluorophores have much more complicated anisotropy spectra, and these really cannot be, I guess they can be explained by quantum mechanics, but I've never seen a quantum mechanical explanation of this that takes into account the real values and doesn't just use assumed values. But for most fluorophores, as you go to shorter wavelengths, the anisotropy goes down, even across the structured absorption band, and you can see it's starting to go up here as we go excitation to the S2 state. So this is a typical anisotropy spectrum, and fortunately or unfortunately, for the indole, for the molecule that we care about the most, because of its dominance in protein fluorescence, it has two transition moments that pretty much lie on top of one another. And this has taken years of research to resolve, but we can say that there are two transition moments in indole. You can assume they're perpendicular to each other, and when you make that assumption, you can calculate that there's a different anisotropy spectrum for one state and the other, but when you can never observe these directly, they have to be calculated. This is what you observe. And speaking of protein fluorescence, this is why the choice of excitation wavelength is critical if you're doing any experiments with proteins. Because if you excite the proteins down at around 290, they might have a very low anisotropy. And it is standard practice in protein anisotropy measurements to get up in 295 to 300 nanometer region to get the highest anisotropy. Why don't we measure the anisotropy across the emission spectrum? And there are very few of these in the literature. I was looking for a better one, but this was the only one I could find. And so this is the excitation spectrum of R6G in glycerol, frozen, essentially solid glycerol. And it has this long flat region. And then you see it actually can go through 0, and it can go down to minus 0.1. So you can cover the whole range of anisotropy values. But if you excite at long wavelengths and measure across the emission spectrum, you find out that it's flat. So there's no information measuring the anisotropy across the emission spectrum, except in some cases of solvent relaxation. And that is, of course, because of Koch's rule. Remember, the molecule is always going to relax to the lowest excited state possible. It's going to emit from that state, and that state always has the high anisotropy. We superimposed an emission spectrum we got off the web for R6G here onto these data, and the experimenters here were very good if they could measure all the way out to such low values of the absorption. But in any event, we really never measured the anisotropy spectrum, and for that reason, many times anisotropies are measured through emission filters, where the emission filter would be chosen to cut off all of the scattered light that would occur wherever the excitation is. What is the effect of rotational motions on anisotropy? So going back to the beginning, we said we were calculating the anisotropy for fluorophores and random orientations, but I also specified that would be immobile, that is, they're not moving. So how do rotational motions link to the anisotropy? Well, we use the same type of calculus that was used before. We assume for the moment it's a single correlation time, and we'll assume that it's a single lifetime in the intensity decay, and we have to do this normal integral, and what it winds up with is something called the Perron equation. It exists in a couple of different forms. This one is sort of this is the normal form that is used for the Perron equation, where the fundamental anisotropy over the observed anisotropy is 1 plus tau over phi. So let's say that phi was very, very long. Well, let's go up to this one instead. Here we have r is r0 divided by the same term, 1 plus tau over phi. If phi is very, very large, that means that's the correlation time for protein rotation. If that is much larger than the lifetime, then this number becomes big, and it drops the R0 value to low value. Conversely, if the correlation time is very short, this becomes a large value and the anisotropy approaches 0. I might have said that a little bit backwards because I was mixing up the two equations, and I apologize for that. But just in your mind, in this equation, think of what the ratio of the lifetime and the correlation time of the protein are, and that will tell you what the measured anisotropy is compared to the initial anisotropy. In the previous lecture, we listed some correlation times for you. Okay, so how do we measure the anisotropy decays? Well, we didn't bring this up in the previous lecture, but if you have a solution where the intensity is decaying, of course, but the anisotropy is also decaying, you can get an erroneous result for the lifetime because the rotation itself contributes to the intensity decay, which we'll see on the next slide. But there's a trick for that. Whenever you're working with biomolecules, if you observe with this magic angle we spoke about before, you will get the right answer. And that's because observation through this polarizer is the equivalent of I parallel plus 2I perpendicular, which is what we said was the total, that represents the total intensity of the sample. This is what I meant by the anisotropy decays. First of all, I'd like to point out that we have no such thing as an anisotropy detector. So all we can do is measure the polarized intensity decays. So let's take a look at that. We've assumed some values here and an R0 value. And for the I parallel plus 2 perpendicular, it's here. But what do the polarized decays look like? Well, let's look at the parallel one. This is the one where you're exciting the sample parallel and you're looking parallel, and you'll notice it starts decaying a little faster than the total decay. So that would be a slightly wrong answer. Conversely, if you're exciting parallel and looking perpendicular, it takes time for the molecules have to rotate before you can observe them. So the decay starts out slower here, and it's the difference between these two decays, which is the actual anisotropy decay, which we've shown over on this side. Another important factor is that there is no connection between the lifetime and the anisotropy decay. And that's another factor. You can only measure an anisotropy decay where there is still significant emission. And by the time you get out to 2 or 3 times the lifetime value, there's not enough light left to measure. So if you had a very short lifetime compared to the correlation time, all the anisotropy would have decayed before you see emission from the longer-lived fluorophore. So the rotational correlation times depend on just about everything. It's very nice because they're sort of linear with molecular weight, but you know, a protein comes in all shapes and sizes, as does DNA, and they undergo association reactions. So let's look at some of those examples. What can give you a heterogeneous anisotropy decay? I'll talk about these two first, which we're not going to discuss today. In the previous lecture, I showed you that the immunoglobulin molecule can have both an overall correlation time and independent motion of the FAB fragments on the ends. So segmental motions in proteins can give you a heterogeneous or not a single exponential anisotropy decay. The fluorophores are not necessarily spherical. Consider perlin, and I should have put the structural of perlin on this slide, but it's a nice, it's a big flat polyaromatic molecule. So it has two different rotational correlation times. It can rotate in plane where it doesn't displace the solvent, or rotate out of plane where it has to displace the solvent. So that's going to give you more than a single correlation time in the analysis. And then we'll see examples today of hindered motion and multiple rotating species. We won't do energy transfer today. So let's look at some typical anisotropy decays. In the case of proteins, you can get almost any, we're now looking at the tryptophanes in proteins, you can get almost any type of anisotropy decay. For liver alcohol dehydrogenase has two types of tryptophan residues in the homodimer, but the tryptophan residues are really rigidly linked to the protein and only show the overall rotational correlation time, which is what the slope is here. In many other proteins, the tryptophan residues are very mobile. So here we have a lumazine protein, and as you can see, most of the anisotropy is lost before you can even start to observe it. And this part out here at longer times is the overall rotational correlation time of the protein. And the short time, this is where there is a rapid decay due to segmental motions of the tryptophan residue, which are hanging off the side of the protein. A second example is going back to something we said, I think we did this in a very early lecture. We spoke about Nexin and how its emission spectra was shifted by calcium. When you add calcium to it, the emission spectra shifts out to the blue, out to the red, and we interpreted that as it being more exposed to the solvent. If this is the case, if in one case, in one form without calcium, the tryptophan is buried, and if the other case, the tryptophan is out in the solvent, we expect different anisotropy decays, and that's exactly what we see. First, we'll take the no calcium case. Where there's no calcium, we expected less freedom of motion, and that's exactly what we observed compared to the case with calcium where the protein has popped out the tryptophan into the aqueous phase. One of the reasons I chose this example is because there's a completely different way of looking at the correlation times, just like there was with lifetimes. Instead of looking at discrete values, here's 50 picoseconds here and 5 nanoseconds here, you can actually do the correlation time distribution. So for these decays, another analysis was done, and for the no calcium case, it results in a single point in the correlation time distribution, which is from this long part of the curve, which is the overall rotational diffusion of the protein. When we put calcium into it, now we have several different components, and once again, at longer times, we see the overall rotational motion of the protein, but at shorter times, there's segmental motions of the tryptophanes, and you have the shorter correlation time components, which is the reason for the rapid anisotropy decay at the beginning for this protein. This was quite a surprise to everyone, so I'll mention this, and it's a reason why we don't like to use the word microviscosity too much anymore. Let's look at the anisotropy decay of DPH in two different environments. One environment is sort of a viscous oil, mineral oil, and the other environment is a dimerysteryl phosphorylcholine bilayer or vesicles. And what do the polarized intensity decays look like? This experiment should have been done at a lower temperature, but it was done a little bit on the warm side. But you see, in any event, that the polarized intensity decays rapidly merge because the DPH is rotating freely and the anisotropy decays to zero where these two curves overlap. The surprising result for membranes, or at least for the homogeneous ones, was that these curves never converge. There's an eye parallel and there's an eye perpendicular, and they're simply different, and they stay different forever for at least as long as you can observe. So this was solved pretty quickly, what the reason for it was, but I'll go through the details just so you can understand. Let's take those same curves we had in the previous slide and show them as the calculated anisotropy decays. In mineral oil, I only had one temperature on that curve, but in mineral oil, they always decay to zero. That's what you expect for an isotropic solution. You don't get that in membranes. The reason you don't, what you find out in membranes is that the anisotropy stays non-zero pretty much forever when you're below the phase transition. So that basically tells you that for some reason, the DPH molecules can't rotate beyond a certain angle below the phase transition. So that's the model that was developed to explain this case. This one on this side is going to be informative for us, but what was developed was the hindered rotator model. And the assumption was that the DPH can only rotate a certain distance when it's stuck between the acyl side chains. And that angle is shown for DPPC, which is a dipalmityl phosphorylcholine, but that doesn't affect the conclusion. And you see that at low temperature, below the phase transition, the DPH can only rotate about 15 degrees before it is blocked by the acyl side chains. But if you get up above the phase transition, the DPH can rotate freely, and that this angle becomes larger. So initially the microviscosity term was used because the viscosity of probes in solvents of known viscosity was compared with the viscosity of probes in membranes, and that proved to be not a valid comparison. Another example of the use of anisotropy decays is given by studies of the integrase from HIV-1 The integrase is the protein that catalyzes insertion of the viral genome into the host genome. Of course, there are other enzymes involved, like reverse transcriptase and stuff, but this is the final step of getting into the host genome. And the integrase by itself tends to self-associate. And this self-association was studied by anisotropy decays. Now, the data here are presented like they were for the annexin in terms of the correlation time distributions. So let's look at this set of correlation time distributions, and it's easier to start at the bottom. What they were adding was a fragment of DNA, unlabeled DNA, to this protein, and they were measuring the anisotropy of the tryptophan, tryptophan anisotropy. So when they had a reasonable amount of this DNA in there, they saw a single correlation time around 14 nanoseconds and a short correlation time. The short ones are, of course, always the segmental motions of the tryptophans, and the longer one is representing the overall global rotation of the protein. So now let's go all the way up to the top where they did the experiment without any DNA. And again, they have a couple short correlation times, and they have one very long set of correlation times up in the range of 100 nanoseconds. And as the DNA is added, this cluster protein starts to dissociate and eventually goes down to the monomer. So this looks like a beautiful experiment, and it is. And I don't want to criticize the authors, but if I look at this region in particular, I cannot understand how that could be measured. No criticism of the authors, but the decay time of the tryptophans couldn't have been more than about 4 nanoseconds, maybe 5 nanoseconds. So by the time you get out to 10 or 20 nanoseconds, all of the intensity is gone. So in principle, they shouldn't have been able to measure these long correlation times. Anyway, this experiment shows what can be learned from self-association of proteins just from the tryptophan anisotropies themselves. Oh, drat. I skipped a slide. And when you skip a slide, you're pretty much stuck. So let's do the associated anisotropy decays, and we're going to try to come back and insert those other two slides. So there's another totally different type of anisotropy decay, and those are the associated anisotropy decays. When I was showing you the anisotropy decay for annexin, what our picture was there's the tryptophan and it's hung onto this protein, and the whole thing is rotating, and the decay is showing you something about whether there's any domain motion in those in that protein or not. But what if you had more than one rotating species in the sample? Well, then you have a different decay law, and it's called an associated anisotropy decay, because one correlation time is associated with one lifetime. So here we have a short 50 picosecond correlation time, which is true for tryptophan in water, and a lifetime of 3 nanoseconds. And then we have another rotating species, which is human serum albumin in this case, has a rotational correlation time of 40 nanoseconds, and we gave it a slightly longer lifetime. What do the anisotropy decays look like in that case? Well, we put the intensity decays down So in one, we had two similar intensity decays, but the anisotropy decay is very different. This is now an associated anisotropy decay, so that the anisotropy you observe at any given point in time is given by the anisotropy of that one component times the fractional emission of the other component, and then the anisotropy of the second component times the fractional contribution of that component. And the best example of this is not a biological example, but a rather artificial one. And what can happen in an associated anisotropy decay is the anisotropy can start to drop down and then go up and increase again. And this might look artificial, but this has been observed in things like the amyloid protein that gets stuck in your brain and makes you forget things. So if you have two different rotating species, you can find a system where the anisotropy doesn't decay to zero, but rather starts to decay and goes back up. And this is because we had the longer lifetime, it had the slower correlation time, and that dominates as you get further out. All right, that's the end of part 9B. I thank you all for your attention and hope to see you next time. And actually, I can't tell you what the topic will be for the next time at this moment. Thank you. Bye.